Okay, so the first thing we want to talk about is natural log derivatives. Now, when you had that sidewalk chalk activity, some of you had this one. Okay, you had that derivative, right, or you had this function, okay? And the derivative of this, if you think about it at the very beginning, the slope is really steep. And also, what do you notice throughout the whole curve? The slope is always positive. So the derivative ends up looking like this. Okay, and as time goes on, this gets closer and closer to 0. And if I graph the other half of this particular function, it may help you remember what parent function that is. Anybody know what this red graph is? 1 over x. And guess what? The derivative of natural log of x is 1 over x. Okay, you'd think it might be fancier than that, but it's not. It's just derivative of natural log of x is 1 over x. So if you're taking natural log of something more complicated than x, like look at example 1 down here at the bottom. Okay, you're still going to do 1 over, so in this case u, and u is not difficult. It just means something other than probably just x. So 1 over u, but we have to apply chain rule. So I have to multiply by the derivative of the inside, which I'm going to write here as u prime. We could write it as du over dx, but it's derivative of the inside. So before I even get to these log properties, I want to go ahead and go straight into this example down here. So for example 1, finding u prime, or finding y prime, the derivative of natural log of something, it's just going to be 1 over that something, which we call the log argument, by the way, when it's what you're taking log of, times the derivative of the inside, which would be how much? 2x. And this is perfect. If this was multiple choice, it would probably be cleaned up a little bit, and maybe that 2x would be moved on top. So I want to kind of simplify as we go now. We've already talked a little bit about simplifying, but that's what the multiple choice would look like. Okay? So actually taking derivative of a natural log is kind of easy. It's really not that bad at all. Some problems get more difficult, and knowing your log properties is going to help you. So let's review some of the stuff that you've already learned about logs, right? You've already learned this. It's way back in the back part of your mind. Okay, you probably won't immediately remember it, but I think it will come back over the next few minutes. Does anybody remember what natural log of e equals?
1.
1. Very good. What about natural log of 1?
0.
0. Very good. Do you remember how to split this up? So you'd think it would be natural log of a times natural log of b, but it's actually plus. And I'm not really going to go into today like why that is. You've had that before in Algebra 2 and Pre-Cal. In the end, you just need to know how to do this. Maybe this word will help you remember expand.
Because it's divided.
Yeah, because it has to do with the fact that natural log is the inverse of an exponent, and we have our exponential rules. Okay, what about when you're taking log, or in particular natural log, of something to a power? Do y'all remember what happens to that power? You take it to the front.
That's the base.
Oh, I gotcha. Okay, so that becomes n natural log of a. Now, do you see how someone might think what we're doing is power rule right here, but we're not even taking derivatives, so just keep that straight. This is just a log property. Okay, what about natural log of a divided by b? How could we expand that? Subtract them. Natural log of a minus natural log of b. And then kind of combining a few of these properties, what would natural log of e to a power be? And that power is n. It would just be that power. So natural log of e squared is 2. And it just combines these properties. So hopefully this is coming back a little bit. Okay, slowly. Notice that these are all natural logs in calculus. We won't ever deal with log log. We'll always deal with natural log, which is log base e. Okay, so let's look at G, because if I asked you to take the derivative of this, it would be like crazy, because the first part would be easy. We just do 1 over that, but then multiplying by the derivative of the inside would be insane. So what we can do is we can split this up into multiple simpler logs. How many logs do you think we're going to split this up into? How many groups of x do you see? 3. Okay, we got this group up here, we got this little x, and then we got the radical. Okay, so let's deal with the numerator first. I have natural log of x cubed plus 3, and then taken to the 5th power, I can put that 5 right in front. I'm not deriving right now, I'm just using that log property. And that's positive. That's a positive 5 because that log argument was on top. Now for the other 2 items, I need to subtract. So I need to do minus natural log x because the x is in the denominator. And I need to do minus for that other part too because that's also in the denominator. What is the power on this piece right here? 1/2. So we're using that log property. The 1/2 is going to come to the front. And I have not derived or anything. I've just expanded. But I hope you can kind of see that if I did need to derive, 3 easy problems, way better than 1 super, super complicated chain rule product and quotient combined. That's what we'd have to do there. All right, we really won't be doing that much condensing. This is really just a practice to make sure you understand the properties. But if I wanted to combine these into a single log, go ahead and try this one on your own. And make sure you're using powers on your variables. Okay, check your answer with mine. Is it coming back a little bit? You thought it was lost. It's still in there. You don't have to write these time symbols. I just did to make a point out of it. Okay, and all of those properties, we're just going to pick them up from time to time, just when we need to make our life easier. So like on number 4, or sorry, on 2, I don't really need to use log properties. It's x times natural log of x. What derivative rule do I need? Product. I have x times natural log x. You have x in 2 places and they're being multiplied. So y prime, using product rule, derivative of the first times the second plus the first times derivative of the second. Remember that derivative of natural log x is 1 over x. And this is fine. This is great. If this is free response, you want to leave it just like that. If it's multiple choice, what do you think the answer would probably be? Yeah, natural log of x, because the times 1 doesn't do anything, and then the x and the 1 over x become just a 1. So that's how the multiple choice answer would be written. Okay, let's look at number 3. Can I use a log property here? It looks like I could, but look at where that 3 is. It's not just to the x, it's to the whole thing. So if you're looking at property D, it's not the exact same thing. Okay, so be careful of that. If we had natural log and then in parentheses x cubed, I could move that 3 to the front. Now, this means I'm going to have to use chain rule. But we're experts on that by now, right?
Yeah.
So I'm going to use, the 3 is going to go to the front, the inside's going to stay the same. The new power is 2. And then I'm going to go times 1 over x. And this is great, probably multiple choice. Instead of times 1 over x, it'd probably be like all over x.
Is the 1 over x part of the natural log rule thing?
It's using, it's like the M&M or using chain rule, it's taking the derivative of the inside.
So is it just like, is it the 1 over x times the derivative of
X, so what could I write at the end?
dx over dx?
Which would be 1. Right. If you wrote a 1 there or a dx over dx, that would be totally fine, because that would be the same. Okay. So we get to example 4. We haven't used a property yet, and if you were sad, then this is your problem. What's maybe something we could do first before we even do the derivative?
Write it prettily.
Yeah, change that radical symbol to a 1/2. And this 1/2 is only to the log argument. So we can use this property D. So notice I'm not even putting y prime. I'm just writing equals over here because I really want to make a point of what I'm doing. I'm not deriving yet. I'm just rewriting. And if you use that log property, then the next step is easier. That's why we did it. Okay? Derivative of 1/2 times this thing is just going to be 1/2 times, what's the derivative of natural log of x plus 1? Think about our rule. 1 over the log argument times the derivative of the log argument. And again, you don't have to write times 1 there. Probably if this was multiple choice, it would be written like that. Okay, I know I went through those 4 examples pretty quickly, so do you have any questions? So because I'm taking derivative of 1/2 times this, it's just like when, like on another problem, when you had 5x squared, your derivative was 5 times 2x. That 1/2 is not by itself, and I'm not even using product rule. You could have used product rule here. You would have done 0 times natural log of x plus 1, and then the second part would be what I've written here. But when a number is one of your 2 pieces, just multiply by that number. If I'd been adding, you're right, that 1/2 would totally go away. Okay, so that's natural log derivatives. Turn the page over, and let's talk about exponential derivatives. This is the easier of the 2. Why? E is for easy. Does anybody remember having this one in the sidewalk chalk derivatives?
We didn't do
Oh, you're right. So we did. It was raining, so we did on it. But does anybody remember having this one? Okay, so let's say no one had it, but somebody did. But what is the derivative way off here to the left? Like, that's pretty dang flat. So I would say the derivative, or the slope, is close to 0. And what happens as x increases? The slope also increases. And it just so happens that it is the exact same graph. Derivative of e to the x is e to the x. Okay, it's just a wonderful coincidence of life. E, that number, it's like pi, the natural number, Euler number. It is, I say E stands for easy. These derivatives are super easy. Okay, let's say it's not e to the x, but e to something else. Okay, like in number 5. Well, you're still going to do, like on this one, in my in general box, e to the u, the derivative would be e to the u. What do you think I'm going to do next? Any guesses? Times what? U prime. It's just another application of chain rule. Okay, so let's immediately go into example 5 here. We have y equals e to the power of 3x minus 5. So the derivative, just rewrite it. Then go times the derivative of the power. What would that be? 3. That's your answer. These are a little bit easier. Okay, probably if this was multiple choice, that 3 would be moved to the front. Your answer would look like that. Okay, so number 6, y equals e to the power of -7 over x squared. Don't think too hard about this one. Just rewrite it first. And write it times. Now, as this is written, what rule would I need to use to derive -7 over x squared? Quotient. And you can totally use that rule, and there's nothing wrong with that, except that you're doing an awful lot of work. Is there another way to write -7 over x squared?
-7x to the power of -2.
Exactly. If you recognize this, and this is going back to the stuff that we've already done before, if you recognize this, you get out of doing quotient rule. If you just love quotient rule, though, do it. There's nothing wrong with that. Okay, -2 times -7 would be +14, and then the new power on x would be -3. And probably if this was a multiple choice, the 14 would be moved to the front, and we'd be calling this all over x cubed. Okay, remember, if it's open-ended, if it's free response, don't simplify. You don't get any bonus points for simplifying. The reason we're simplifying is for multiple choice questions. Okay, so that's how you derive natural log of x and e to the x and other things. There are 2 examples here then they both happen to have natural log in them instead of e, but really there could be any problems here with implicit differentiation or tangent lines or anything we've already done with derivatives we can do with these. So let's just do a couple of examples. So like on number 7, implicit differentiation. Remember, this is when we take derivative with respect to x. So this is going to be largely review right here. Derivative of x squared, 2x. Okay, now I'm going to take derivative of -3 or -3 times natural log of y. So this is kind of like what we did earlier. I'm going to go -3 times the derivative of natural log of y. Y'all remember from the front? 1 over y times dy over dx. Anybody wanting to write y prime there? That's okay. A lot of people want to do it as soon as we get into this, like because of the whole u prime thing. We don't like to, on implicit problems, write y prime. It's just too hard to tell the difference between y's and y primes when they're all mixed up. Okay, moving on. Derivative of y squared. 2y, again, times dy over dx equals what? 0. And from here on out, this is just like the other problems that we've seen. Okay, so box the ones, just start at the dy over dx and go all the way back until you're not multiplying anymore. Okay, so that 2x is the only thing that gets moved over to the right. On the left, I'm going to factor. And I'm going through this part quickly just because this is review. And then divide. And this is messy. I'm not going to go over simplifying this one today. You could simplify. See how there's a fraction within a fraction? That's a little yucky. We're not going to worry about that right now. I feel like we've done enough new stuff today. And then in our last example, we have to find the equation of the tangent line. What do you need to write an equation of a line? You need a point, which means you need an x and a y, and you need slope. Okay, we are given the x. Okay, so it's going to be 1 comma something. How are we going to find y? Plug it into the original. I'm going to go ahead and do that now. And this is why I wanted to review some of that stuff about natural log on the front, because this natural log of 1 squared, that goes away, and the y value is 3. How are we going to find slope? Derivative. Remember, when in doubt, take the derivative. Derivative of 3x squared, 6x. What is the derivative of this minus natural log of x squared? So we could do this a couple different ways. I want to show you guys how most of you, I think, would do this. You'd go minus 1 over x squared times 2x, and this is totally fine. I am going to show you how you could have used a property here. Remember x squared, that 2 can be moved to the front, and so you could write it like this. And then you're just multiplying by 1 at that point. It turns out to be the equivalent. So most of the time when you use a log property, it's not that if you forget to, you're going to get the answer wrong. You just do a little bit or a lot more work. Okay, so that's the derivative. In order to find the slope, remember we need to plug 1 in. This is just the same stuff we've been doing. And then we write our line.